Hello everyone, thank you for joining. We're continuing with Einstein's special theory of relativity, and then in the previous video we looked at the situation where a cyclist is traveling near the speed of light, and we have two observers at point A and B, and let's call this cyclist C. So, but little c here indicates the speed of light, not to be confused with capital C. Right, according to, if you are at C, if you're the cyclist, and if you're observing this motion here, the light wave from B will seem to you as c plus your speed, which is 1.9 c, and the light wave from A would be c minus 0.9 c, which is 0.1 c. Okay, right, and that's very intuitive because we are now aware of Galilean transformation for position and speed, and that makes sense, right? But the problem is the experiments. The experiments show that the cyclists observe the speed of light here to be only c, not 1.9 c or not 0.1 c. So somehow speed of light in every inertial reference frame seems to be 3 times 10 to the 8 meters per second. Now that contradicts with our intuition of the movement and the motion, right? So that the light travels at 3 times 10 to the 8 meters per second in every inertial reference frame, right? So how can this be, right? So let's consider an experiment, a thought experiment, right? Okay, so we want to make a measurement. We want to measure the speed of the cyclist from a tree to the lamppost, and S represents a stationary person. S dashed is a car driving at a constant velocity faster than the bicycle, making the same measurement. And if you look at the S frame here, all you see is that, as you'd expect, initially the bicycle aligned with the tree, and then finally it is at the lamppost, right? And it takes, let's say, delta t, right? Okay, and then the car is making the same measurement, but this time the tree and the lamppost doesn't seem to be stationary because there is a relative motion with respect to the car. Tree and the lamppost are moving in the opposite direction. So what happens here is that the distance, which I called x here for S, will be much shorter, which I will call, let's call it x dashed. Okay, so distance that the car reaches or aligned with the lamppost. Okay, and we are interested in u and u dashed, right? So we know the relation, the speed is distance over time. Now if you look at it, we know that delta x is different for these two different observers. We have x there and x dashed there, right? So delta x is clearly this difference. Well, I should, to be consistent, call this delta x and delta x dashed, let's say, yeah? So they are different. In other words, delta x is not equal to delta x dashed. And we know our intuition from Galilean transformation of velocity, u is not equal to u dashed. Okay, so which makes sense. It both takes the same time for the measurement, and then delta x is different than delta x dashed. Therefore, looking at this relation, u is different than u dashed, right? But the claim here now, not the claim, actually, experimental facts shows that u must equal to u dashed if we replace the bicycle with a light, right? So let's say that we have a tree here and a lamppost again, but this time instead of cyclist we have a photon traveling from there to there, right? And the experimentals show that the two different observers, the stationary observer and the observer on a car, they will perceive that the car is traveling with some velocity v, and they will, both observer will perceive the speed of the photon to be c. Well, we know the distance will be different because the car is traveling. So we have u is equal to delta x over delta t. And we're saying that that's equal to u dashed, by the way. This is where the challenge is. So if this is different, delta x is different, that means the time must also be different, right? So the only way u can equal u dashed is that if delta t measured here is different than delta t measured there, which I'm going to call a t dashed, yeah? Okay, so if the time it takes the light to move from tree to lamppost in one reference frame is delta t, the other one will have to be delta t dashed for u dash to equal u. So in other words, that we are saying that the time must be different. So delta t is not equal to delta t dash. Now this is a crucial point we need to, I think we need to pause here for a moment and think about it, because we're not talking about, consider that you have two people doing the same work. So you have some work on a table and two people are, the first person is here, other one is here, and they are doing some work here. Now person A is much faster. Because he's working faster, it will take less time. But what we're talking about here is something completely different. It is not about a person doing something faster, it will take less time. It doesn't say anything like that. Now, this is a statement about the nature of time. I mean, we use this question, what time is it? And we know the answer if you have a clock. But what is time is we only know a few things about it. But one thing we need to be careful, the reason this is shocking is not because, as I said, the one person working faster than another will take less time. It has nothing to do, this is a statement about the nature of time. Time is a thing which slows down if we travel near the speed of light. So this is a, I'll say explicitly, it's a property of time. Okay, so it's a property of time. That's why it's quite shocking. Yeah. So in other words, going back to Galilean assumption, I don't know if you've noticed this before, but the Galilean assumption, we never consider time slowing down or anything, yeah, and which is very intuitive to us, Galilean transformations. So the assumption, well, something must be wrong with our assumption that we made about the nature of time. So the nature of time is quite different than what we were expecting it to be. Okay, so I think I haven't said much about Einstein's theory of relativity, and I keep saying that we will do it next video. But I think what's really crucial is the special theory of relativity, the mathematics of it is really easy. There is nothing challenging about it, yeah? It is very much challenging conceptually. So if we get the principles on which this theory is based on right, then I think we are in a better position to understand both special and general theory of relativity. And I think I'm going to end this video to leave you with a question that let's think about this very interesting relationship. And let's keep this in mind as well. We're not talking about if you do something quick, it will take less time. It's a very different statement. It's a statement about the nature of time. Somehow it slows down, literally, yeah. Okay. Well, yeah, so I think maybe this is a good point to stop so that you can start thinking about this new concept of time. And then next video, let's reconstruct the space and time and how Einstein did it. And then that will lead to Einstein's equations for the equations of special theory of relativity, okay? Well, I hope you enjoyed it, and I look forward to seeing you in my future videos. Thank you.